What a wonderful day to be an electron, fully sentient and aware of my existence. Oh, hello, other electron. Where are you and why are you here? Where I'm from? I, I don't know. Do you? No. This video is gonna be one hell of a yap fest. And just like anything related to theoretical chemistry, it's going to be dry and bland, so bear with me. Let's begin with electron configuration and start off with the introduction of the atomic orbital model. We will be using the Schrodinger's model in this case, with the sphere that has a plus being the nucleus and the area surrounding it is the space where electrons are most likely found, and said area can also be called atomic orbitals, or as we will abbreviate from now on, AO. Currently there are 5 AOs found: AOS, AOP, AOD, AOF, and AOG. Each orbital houses more electrons than the previous, specifically a difference of 4 electrons per. I don't really know where to put this, so I'll tag the formula for the maximum amount of electrons in a certain layer here. E equals 2n squared, with n being the layer. Tying all together, these informations are used to determine the electron configuration of an element. An electron configuration shows the arrangement and classification. The number in front, or n, is the layer. The letters behind shows the according AO, and the exponent is the amount of electrons in that orbital. So for example, 2p3 means that it's the AOP in the second layer with 3 electrons inside. All of these configurations follows rules, of course, with them being written in the order from low energy to high energy. The energy levels are ranked using the Klekowski or Aufbau rule, showed in this chart. The states crossed by the same red arrow have the same energy value, and we prioritize ranking from lower layer to higher layers. Now, it wouldn't be chemistry if there are no exceptions. In here, the exceptions to this positioning is chrome and copper, which follows the subsaturation and saturation law, respectively. So chrome, its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. So instead of the last two of the configuration being 4s2 and 3d4 like the positioning rule, the 3d4 takes 1 electron, turning it into 3d5. Since the amount of electrons will claim half of the orbital, we could call it as the subsaturation law. With the same idea, copper follows the saturation law, making the two last configurations being 4s1 and 3d10, making a full AOD instead of a full AOS. Why do they do that? It's because the configuration would be more stable like that than if they follow the rules. Enough with configuration. Let's add more detail into positioning of electrons with the use of these cells. Different from configuration, each cell is an orbital, and an electron is symbolized by an arrow pointing upwards or downwards. More on this later on. This will show you specifically how electrons are positioned in an orbital, but it will not, however, show you the layer that orbital is in. Side note for positioning electrons, it will prioritize single electrons per cell over pairs per cell, arrows upwards before downwards. Why single electrons are prioritized over pairs? Electrons are negatively charged. Things that have the same charge will repulse one another, and it will cost more energy to keep pairs of electrons than to keep a single electron, which then makes the orbital less stable. To make this clear, let's have an example. We will take a configuration of P4. P has the maximum amount of electrons being 6, so it has 3 cells, Px, Py, and Pz, being in order. It has 4 electrons, so there's 2 singles in Py and Pz, while a pair in Px. Now to the main part after this whole sing and dance. Quantum numbers are used to determine the exact position of an electron. Not configuration, not orbital, electron. There are 4 quantum numbers that makes up the coordinates of an electron. First is a very familiar one. N, or the main quantum number, details the electron layer an electron is in. N is of course numbers like 1, 2, 3, and so on. Next one is the side quantum number, or L. L shows what AO the electron is in. LS equals 0, LP equals 1, LD equals 2, LF equals 3, and LG equals 4. Third is the specific orbital of an AO. The symbol for it is ML. ML equals negative L all the way to positive L. And finally, we have the spin numbers, which are the arrows mentioned earlier, with upwards being positive 1/2 and downwards being negative 1/2. Despite being called spin numbers, they're not really spinning. Yeah, it's actually just a faster way to describe the angular momentum of an electron. Let's process this with an example. We will describe the 7th electron of a configuration of 3d7. 3d7. 3, so n equals 3. D, so L equals 2. That's 2. Onto the tough ones. We could envision a 1/5 cell. L equals 2. So we have the cell's name in order of -2, -1, 0, 1, 2. Place each electron single first, and then we have 2 spares. Place those spares in the first 2 cells, and we get this model. So the 7th electron, it is, to this model, the downward arrow in the second cell. The second cell has an ML value of -1, so it's -1. And the arrow is downwards, so its spin, or MS, value is -1/2. So you can determine the exact position and velocity of an electron because Mr. Walter White says you can't. Alright then, we can just use a function to describe the probability of its appearance in a function then. But that's function. Where's wave? Remember the de Broglie theory? That's the wave part for you. This function is called psi. And in quantum chemistry, psi squared will give us the probability of finding an electron in a certain point. The wave function that we have here is 2-dimensional. If we draw the function in 3 dimensions, we get the shapes of the orbitals. First, let's examine the s orbital. So, the 1s orbital, considered as a circle universally. However, it's not. Since the Heisenberg's law contradicts it, the circle is actually a simplified version of the orbital. So imagine you have a camera that could picture electrons. So it's like this with a random dot. Now you take 100 more photos, stack them up, and we get this whole map of electron positions. Now you see that it makes up a circle. So the probability of finding an electron is very high inside of this circle or orbital. That's the 1s orbital. Now the 2s orbital, and we get something that looks like a donut. The inner circle is the 1s orbital. The outer ring is the 2s orbital. And this blank space in the middle of these 2 zones, we call them nodes, where there's absolutely no electrons. In conclusion, the s orbitals are all circle-shaped, and from the 2s orbital onwards, there will be nodes. So for each orbital n, there will be n-1 nodes. But why are there nodes in those higher s orbitals? They can't just teleport now, can they? Well, electrons, once again according to de Broglie, also have wave properties. Waves that move sinusoidally will, at some point, reach the intensity of 0. In that 0 point, there is currently no way to detect electrons there. To put it simply, take a guitar string. It could go up and down, but at some point, it will remain still. Or so the camera that takes pictures of the string thought. It is actually still vibrating, but it's so indistinguishable from being completely still. Next up is the p orbitals. As you can see, each loop of the H-shaped p orbital is a different sign for a wave. It's not actually their electric charge, thus the node between each loop is the 0 value when transitioning from positive to negative. Similarly, with the 3p orbital, a node between what looks like the 2p orbital and another separating the negative and the positive waves. Thankfully for wave functions, exercises would usually provide formulas for them. For an equivalence exchange for this long yap, exercises will be relatively short this time. If you decided not to look at your periodic table and do the configuration of vanadium by yourself, pat yourself in the back. Anyways, we'll start by filling 23 electrons into each orbital accordingly. 1s2, 2s2, 2p6, 3s2, and 3p6. After that, we still have 5 electrons to spare. Using the Aufbau principle, we get the 2 remaining configuration, which is 4s2 and 3d3. Next up, third electron in the 3d orbital. We would get the value of n, which is 3, and L, which is 2 immediately. Now we draw 5 cells, filling each cell with an electron, resulting in the third electron inside the third cell, which has the ml value of 0. This is a single electron, so the spin value is positive 1/2. Now, I know this looks bad. First of all, it's going to get worse. Second, it will be less complicated if you boil it down. The state has L equals 0, so this is the s orbital. N equals 3, so the amount of nodes is n minus 1, so it's 2. To determine the position, we need to calculate r, which is the radius from the center to the node. The function for position, as we have discussed, is psi squared. So we'll do just that, and we get the equation of psi equals 1 divided by 81 squared multiplied by 3 pi multiplied 1 divided by 0 cubed multiplied by 27 minus 18 times sigma plus 2 sigma squared multiplied by e by the power of negative sigma divided by 3. Nodes have 0 electrons, so the psi value equals 0. Now for the equation to be 0, 27 minus 18 sigma plus 2 sigma squared must be also 0. Since the others could not be 0, we solve this equation and get 2 sigma values, which are 7.1 and 1.9. Plug it in the given formula and we get the distance is 1 or 3.6 angstroms, which are the position for each of the nodes respectively. Congratulations for making it to the end of this video. Stand proud, for you may have an attention span longer than most of the people of your age. For the next video, we will be talking about the multiple electron system and the Slater's rules.